All right, in this video, we're going to talk about the dot product of two vectors. In previous sections, we've discussed how you can perform vector operations such as scalar multiplication or adding two vectors together, but we never talked about multiplying two vectors together because technically it doesn't exist. What does exist, however, is something called the dot product. And the dot product is defined as u1v1 plus u2v2, as you can read, where these are the pieces of vector u, the components of vector u, and the components of vector v. We usually discuss it in terms of xy, so you can do it this way and just call it x1, x2 plus y1, y2. So in other words, so in other words, it's the product of the x's plus the product of the y's, the product of the horizontals plus the product of the verticals. One thing to note, however, you will end up with a scalar, in other words, just a single number at the end of this problem, not a new vector. So when you take the dot product, you end up with a scalar. Now, before we talk about actual calculations, actually doing that, let's just quick talk about some properties. U dot v is the same as equal to v dot u. In other words, the dot product is commutative. You can do it in either order. 0 dot v, and this is, by the way, the zero vector, not the number 0. It would work the same way, but this is called the zero vector. The zero vector has horizontal and vertical components 0. So you take the dot product of the zero vector and any vector, you get 0. The dot product is distributive, so you can take the dot product of u dot, the sum of two vectors, and it ends up being the sum of the dot product. So you can think of it that way. Taking the dot product of a vector with itself is an alternate calculation of a magnitude. In other words, you can take the dot product, you get of a vector in itself, you get the magnitude of a vector squared, and then you can't really distribute into a dot product, but you can, if you have a scalar multiple of a dot product, you can scale one vector or the other, and then take dot products. So those will come up from time to time. Definitely handy to know the properties of dot products when you're going to calculate dot products. That said, let's actually go ahead and pardon me, calculate some dot products. So really simple process. You multiply the x coordinates, not coordinates, components, and you add to it the product of the vertical components. And as always, there is a plus sign in between them. So you get 8 plus 15 equals 23. Pretty straightforward. I don't think I need to break them down like this every single time, but I'll just zip through these real quick for you. So you get 2 times 1 plus negative 1 times 2 for a 0 dot product, and now you get 0 times 4 minus 6 equals negative 6. So that's how you calculate dot products. Really straightforward. Really, this process should become automatic very quickly because it will come up in a lot of different uses or a lot of different things we do over the next couple of days. So a couple more dot product using the properties this time to make some calculations. We'll start off with 3 different vectors, u, v, and w. You see their components listed above. And we're just going to make some calculations and using those properties. Now, this one uses the dot product of u and v, so let's go ahead and find that first. Here's u and v. The dot product of u and v is negative 2 minus 12, or negative 14. Now, the one nice thing about doing that first is you can now just plug that right in here. Negative 14 is the dot product. Now take vector w is 1, negative 2. What happens here is the dot product, this one is, since it's a scalar, the dot product is a scalar, it is now acting as a scalar multiple of vector w. So what you'll get is negative 14, positive 28, because you're using this dot product as a new scalar value for an additional vector. So that's why you'll notice this example has an answer of a new vector, because the overall problem is a dot product scaled into a vector. Whereas this one, the overall problem is a dot product. One of the vectors is scaled, which, by the way, you could take the dot product, let's just do it that way, of u dot 2v, which is 4, -8, just taking this and scaling it. And now you take this dot product of -4 minus 24, which gives you -28. But what's nice about this is it proves one of your properties, not proves, shows one of your properties. One of the properties said that if you scale a dot product, it is equivalent to the dot product of one of the vectors scaled, which should look something like this, u dot 2v, u dot 2v. So what can happen is we can rewrite it this way. We'll rewrite this way using this little property. We'll take this 2 out front. So one of these properties in use, we already know the dot product of u and v is -14. So it shows that you can either do it longhand or use the property to come up with the same value.